Hi, my name is Monica, and in this video I'm going to tell you how to compute a private key for RSA digital signature. Basically, this is just you have to compute inverse of E, public exponent, in the right ring. That's all. So computing private key is basically just computing inverse element. Okay, so let's start with some kind of, I will show it to you with example. Okay, so let's say that we have P and Q, some kind of small numbers, so it will be easy to compute. 23 and Q is 37. Then when we compute phi of n, we compute it as P minus 1 times Q minus 1. So in our case, we have 22 times 36. That gives us 792, and it also can be written as 2 times 11 times 6 squared. So why I need it? Because our public key, we pick it in such a way that it has to, the greatest common divisor of E and phi of n has to be 1. Right? So greatest common divisor of E that we have to choose, and our 792 should be 1. If it's not 1, then we cannot compute private key. So let's say that we use E equal 17. So now definitely it's true, right, that the greatest common divisor is 1. Now we are going to use Euclidean algorithm, in fact extended Euclidean algorithm. So first part of Euclidean algorithm just helps us to compute the greatest common divisor. Yeah, we know it's 1, but we need this first part of this algorithm. So we have 792 is equal, and how many times we can fit 17 in 792. So it can be written as 46 times 17, and we have plus 10. Okay, now we move it to the next line. So 17 and 10. So 17 can be written as 1 times 10 plus 7. And then this goes here, this goes here. Then 10, we can represent it as 1 times 7 plus 3. Then again, we can write it as 7 as 2 times 3 plus 1. And in the next step, of course, if we have 1, just some students like to kind of finish with 0 here at the end. So of course, 3 can be represented as 3 times 1 plus 0. So this just confirms that the greatest common divisor of 792 and 17 is really 1. Okay, so this is our, so the last one before 0, this is the greatest common divisor. Okay, of 17 and 792. Now, what we need here, so this is a Euclidean algorithm. Now we need its extension. Okay, so I will have to clean this because I will not have enough space. Now let's use it. So 1 can be written as 7 minus 2 times 3. 3 is 10 minus 1 times 7. I just move things on the left side of the formulas. Then 7 is 17 minus 1 times 10. And 10 is 792 minus 46 times 17. Okay, so I'm going to use this formula. Now I want to express 1 as linear combination of 17 and 792. If you don't know what is linear combination, don't worry, you can just follow it step by step. Okay, so we want to represent 1 in a different way, right? Okay, so let's clean this part. I really want to keep it on one page. That's why I'm not using new whiteboard. Okay. So now let's start. So this is the extension of the Euclidean algorithm. So actually now we are using extended Euclidean algorithm to compute it. So 1 is 7 minus 3 times 2 times 3. Now we replace, so the next one is 3, right? So we replace this 3 by the formula on the right hand side. So we have 7 minus 2 times 10 minus 1 times 7. Now the idea here is that you don't multiply numbers, kind of. So we have what we have here. So we have 1, 7, and minus 2 times minus 1 gives us 2. So we have 3 times 7 minus 2 times 10. And now what we want to replace here, we want to replace 7. So this is what we replace in our formula. So we have 3 times 17 minus 1 times 10 minus 2 times 10. Put some order here. So we have 3 times 17 and 3 times minus 1. So we have minus 3 and we have minus 2. So we have minus 5 times 10. And then we replace, next one is 10. So we replace 10 in our formula. Almost done. 3 times 17 minus 5, 792 minus 46 times 17. So what we have total here, so we have 3 times 17, then we have minus 5 times minus 46. So that gives us 233 times 17 minus 5 times 792. And we are done. So there is nothing more to replace. So what we have here, so we are looking for inverse of 17. So inverse of 17 is just next to 17. So this is our inverse. This is our D. So this way of computing those things is for those of you who don't like to remember formulas. Okay, now always you can verify your result. So how to verify your result if this is the right D? So we just simply multiply 233 times 17 modulo 792. And of course you want to have 1 as result. So in this case, you can use calculator to verify my result. So this is 1. So because this is 1, it means that the D was computed in the right way. Okay, so there is another way for those of you who don't feel comfortable with this way and you prefer to remember formula. So what we have to remember from this slide is here we have some values. So we will need this to use it in some kind of table. So first part of the algorithm, you have to use it in any way. If you have some programming experience, you can imagine how to write program for this part, right? And how to store those values somewhere. So we need this 46112, okay? So we make a little table. So we make a little table. Here we have something that we call Q minus 1. Here we have SI and TI. Now we always write 0, 1 here. We cross out this. We will not go to use this part. Here we always put 1 and 0 and 0, 1. So this is like getting ready for the computations. Now here we put those values. So we've put this 46, 1, 1, and we had 2 there. So now we can actually see how many iterations we have. So we have 2, 3, 4, 5. Now, there are formulas how to compute next SI and TI. So those formulas are like this. So we have TI is given by the formula TI minus 2 minus QI minus 1 times TI minus 1. And the same for SI. It's very similar formula. Minus QI minus 1 times SI minus 1. So actually for inverse, we don't even need SI, just kind of to show you the whole algorithm. So now we can compute. So we have 1 minus 46 times 0, so this is 1. Now we have 0 minus 1 times 1, so we have minus 1. Now we have 1 minus 1 times minus 1, so that gives us 2. Now we have minus 1 minus 2 times 2, so that gives us minus 5. Okay, now we compute TI. So here we have 0 minus 1 times 46. Okay, so we have minus 46 here. Here we have 1 minus 1 times minus 46. So we have 47. Here we have minus 46 minus 1 times 47. That gives us 93. And here we have 47, like 2 back, minus 2 times, so minus 2 times minus 93. That was minus 93, minus 93. Okay, and that will give us 233. So you see, this is the inverse. Okay, the inverse. This is our D. What is this minus 5? If you will like go back in the video, you will see that actually 1 can be written as 233 times 17 minus 5 times 792. So this is this minus 5. Okay, so you can implement it very easy, and you can compute it in your program, right? Because nobody computes private key of RSA by hand. Okay, so this is first way. You can use this extended Euclidean algorithm, and the other way is actually it's just easier because you can use Eulers theorem. Okay, so now with Eulers theorem, so we have something that we call, we have a given credit to Fermat. Okay, so we have Fermat little theorem. So if P is a prime number, and the greatest common divisor of A and P is 1, then A to power P is congruent to A modulo P. Now, the generalization of this theorem is Euler's theorem. And it says, if greatest common divisor of A and M is 1, then A, Euler's phi function of M, 1 modulo M. So this is what this theorem says. Now, if we go back to RSA, what we want to compute, we know that we have greatest common divisor of E and phi of N is 1. What that means that we replace A by E and we replace M by phi of N. Okay, so this is this, this is this. So our theorem with those names for RSA will look like. So we have e to power phi of n 1 modulo phi of n. And so it's easier to work with m. So actually phi of n, let's call it m. And in our case, it was 792. Okay, so now we need phi of m. So phi of m, we need a factorization of 792. Okay, so 792 by 2, 396 by 2, 189, 1987. I pre-computed it, don't worry. I don't count so fast. Okay. 198 by 2. This is 92. This is by 11. So we have 9, 3, 3, 3, 1. Okay. So this is our m. M is represented as 2 to power 3 times 3 squared times 11. Okay, so now we can compute phi of m. So phi of m is 2 to power 3 minus 2 square, 1 less, 3 square minus 3 to power 1, 11 minus 11 to power 0. So we have 8 minus 4, that gives us 4, 9 minus 3, that gives us 6, and 11 minus 1 gives us 10. So this is 240. Okay. Okay, so we need this. And now what we have to do, we just have to use our formula. So our formula, the green formula, okay, this one. Actually, I can write for you general formula for this. So if you will write e to power phi of m 1 modulo m, where m is phi of n, public parameter n in RSA. So we have e times e phi of m minus 1 congruent to 1 modulo m. Okay, so if you go back to RSA algorithm, you will see that what we have here, this is our d. This is our d. So you have actually the general formula how you can compute the d. So you can kind of like forget this part of the video, and for your application, you can just write this formula. That let me clear this. Let's use new whiteboard. So the formula for your d is e to phi of m minus 1 modulo m, where m is phi of n. Okay, so now we computed. So our d, e was 17, phi of m 240 minus 1 modulo 792. And now if you use calculator, you will see that that gives us 233. So exactly the same result as before. So now you have like 3 ways to compute inverse of E, RSA private key. One is just by hand, so maybe for your exams, and 2 other are using formula, so we can implement it, and you can use Eulers theorem, right? This formula in your program to compute this key. Thank you very much for watching, and have a good one.